Share. Hide. How do I do this? Yeah. Oh my god, what does this thing come out now? Yeah. So why is it there's something funny? I don't know. Okay, it's recording, no? It's recording. So yeah. So let's begin. So we continue with where we left off in the last chapter, and just make the screen not complete full screen, but just so that I can have the taskbars. So we continue from where we left off, and let me share my screen. So we use the fact that a commuting family of operators has a common eigenvector because we are working over a complex field. Now, what happens is that when you have a commuting family of unitary operators, then we know that they can be simultaneously, unitarily diagonalized. If you have a commuting family of Hermitian operators, then we know that they can be simultaneously, unitarily diagonalized by proving that two Hermitian commuting Hermitian operators, you do it for two and then you just generalize it. Now, when you take normal operators, you need a you need a small technical lemma, and this technical lemma is called the Fuglade Putnam theorem. If A and B are normal matrices, it doesn't even have to be the same size, and X be a matrix such that AX and XB are defined and of the same size, then AX equal to XB if and only if A star X equal to XB star. That is if so. This is in particular, it would be interesting to take A to be equal to B. Suppose I take A and B to be equal, then X will have the same size as A. Then the theorem says that if X commutes with A, then X commutes with A star also. So, for example, this is the Fuglade-Putnam theorem. We won't need it right now. The reason why I put it here is because in the MA106 course, we proved that two commuting Hermitian matrices can be simultaneously unitarily diagonalized. From there, we concluded that every normal matrix can be unitarily diagonalized, and a unitary matrix can be unitarily diagonalized. But now the question is, when you have commuting normal matrices, you need a slightly more. You need this one extra. You need to go this extra mile, and so I included this. So since we will get back to this when we need it, so it was more like an exercise. So if G is an abelian group, G is a finite abelian group, and rho from G to GLB is an irreducible representation, then dimension of V is 1. Because we have seen that for an abelian group, the irreducible representations are one dimensional. Okay. There are certain exercises in Steinberg. We have discussed this dihedral group already, and then exercise 2 on page 23 has been discussed. Exercise 3.3 on page 24. If phi and psi are two one-dimensional representations, then phi and psi are equivalent if and only if they are equal. Equivalence and equality are one and the same for degree 1 representations. And this is a completely trivial exercise, but anyway, it is here for records. And then the next exercise is about the dual group of a cyclic group, and the dual group of a cyclic group is again a cyclic group. So that again we have discussed this, because when you take a cyclic group and I look at the degree 1 representations, I can send the generator wherever I want. So I pick a generator, and you have n choices for the generator. So that's the idea. So this also we have discussed in chapter 0, and that's also exercise in chapter 0. And in chapter 0 already I mentioned that the dual group is again a group under pointwise multiplication. This also we have discussed. And we also proved that the group and the dual group are isomorphic as groups. And we also discussed that this isomorphism is not canonical. Now the next thing is that G and G hat are isomorphic for finite abelian groups. This is easy. Try it out. That's an exercise. The next thing is conjugate and contra gradient representation. Suppose phi from G to GLNC is a group representation. Then you look at the map phi bar from G to GLNC, where you take phi bar of G is you take phi G and then take the conjugate. In other words, each entry you take the matrix phi G and you conjugate every entry of the matrix. This is called the conjugate representation. This is obviously a group representation because complex conjugation respects addition and multiplication. Now, the question is there a natural basis free way to define a conjugation on a complex vector space? Now, we have seen when we were discussing complex geometry that if I just say that V is a complex vector space, there is no natural way to define a conjugation operation. If you have a J operator, the J operator on a real vector space is like multiplication. If I have a real vector space of dimension 2n, then what is the J operator? J is a R linear map such that J squared equal to minus I. Remember that complex structure that we discussed when we were doing complex manifold? We don't need that, but that's just a question for you. But if I just say the letter V, if I just say V is a vector space, V is a complex vector space. There is no way to canonically define a conjugation map. On Cn you can define, take a vector Z1, Z2, Zn, and I can conjugate it, Z1 bar, Z2 bar, Zn bar. Of course, complex conjugation is not a linear map or anything like that. It's R linear, it is not C linear. But on a general, so this idea of phi bar, that is a conjugate representation, that is only when the representation is concrete, as a representation in terms of matrices. That is, it is a group homomorphism from rho to GLNC. That is the idea. Now we take the other one, the contra gradient representation. What is the contra gradient representation? Sure. Yes.
But can't we do something similar? As in, like for example, in the case of vector bundles, if we have a complex vector bundle, then we can look at the corresponding conjugate bundle.
How do we do that?
I think
we'll discuss that later.
Yes.
I don't think it is straightforward. So now the question is that now we take a map psi from G to GLNC, and we want to define the conjugate transpose. That is, what you do is that you take the group homomorphism phi and you calculate phi of G inverse. Now, if I don't put the inverse, if I just take phi of G and put a transpose, it will not be a group homomorphism, it will be an anti-homomorphism. So to get a group homomorphism, you introduce a G inverse and you get phi of G inverse T. Now that's a representation. That is known as a contra gradient representation. Note that if the representation lands up in say ONR, for example, you don't get anything new. If the image is ONR, we get nothing new because it's an orthogonal, because phi of G is orthogonal, and so G transpose is G inverse. So phi G transpose is the same as phi G inverse. One can of course replace the transpose with the adjoint. To define this for an abstract vector space, to define the adjoint, you need a abstract vector space and you need a Hermitian form on an abstract vector space. Then you can do that. Now again, give an example to show that phi and phi bar need not be equivalent. Already for a degree 1 representation, phi and phi bar may not be equivalent. Okay. So Now suppose if you take a suppose I take a degree 1 representation and I take another representation phi, then chi times the product is again a representation. The degree of chi phi is the same as the degree of phi. But chi phi and phi need not be equivalent. You try doing something with a sign representation on this. There's another exercise from Steinberg's book. The next exercise is from Lederman, page 63, Walter Lederman's book on Introduction to the Theory of Group Characters. If a group G has k distinct one-dimensional representation, suppose it has k distinct degree 1 reps, then k must divide the order of G. In fact, the degree 1 representations are in bijective correspondence with the abelianization of the group. Okay, so suppose for example, if you take a map phi from G to C star, a degree 1 representation, then phi must factor through the abelianization. The abelianization is G factored with a commutator subgroup. And let eta from G to the abelianization with a quotient map. Okay, with a quotient map. The kernel of phi must contain the commutator subgroup. So we have a commutative diagram from G to the quotient eta, and from G to C star, and from the quotient to C star. There is a unique homomorphism phi tilde such that phi tilde composed with eta is phi. Now if phi 1 and phi 2 are two distinct one-dimensional representations, so that phi 1g is not equal to phi 2g for some g. That means obviously phi 1 tilde g bar is not going to be equal to phi 2 tilde of g bar by this very definition. So that phi 1 tilde and phi 2 tilde are also distinct. So the dual group of A hat is greater than or equal to k. Conversely, if phi tilde is in the dual group of A hat, then phi tilde composed with eta is a degree 1 representation of G. So we get the other inequality. But we know that A and A hat are equal in terms of cardinality. So the cardinality of A is also k, and A divides the order of G because A is the abelianization. So the result. So we have done this exercise on page 63 of. Is this clear? What we have done? This idea of going through the abelianization, and it says that the one-dimensional representations of G are in bijective correspondence with the abelianization. This is going to be very useful to find representations actually. Clear? Everybody?
Yes. Yes, sir.
Now suppose if n is a normal subgroup of G and then eta from G to G mod n is a quotient map, then you take a representation of G mod n, and we compose this representation with eta, you get a representation of G. This is a very important construction of trying to lift a representation of G mod n to a representation of G, where n is a normal subgroup. Of course, if G is a simple group, then it doesn't have any normal subgroup, and so we can't do this at all. So this process becomes interesting only when G has a bunch of normal subgroups, then we can play this game. More generally, if you take any group, a surjective group homomorphism from G to G prime, then basically G prime is G mod n. So out of a representation of G prime, we can get a representation of G simply by composing it back via eta. Now this more general situation is also important because in many interesting cases, what you do is that you compose with an automorphism. What if this eta is an automorphism of G? Then again, via compositions, you can do the same thing. Via compositions, you can get a new representation. We'll use these ideas frequently later. Now let's come to the representations of the dihedral group of order 10. We already have two representations, the trivial one and the geometrical one, described in terms of 2 by 2 matrices. Right? So we already have two representations of degree 1, of degree 1 and one of degree 2. Now the dihedral group has a normal subgroup of order 5, right? Call this normal subgroup N. So that G mod N is a cyclic group of order 2. Because G mod N is a cyclic group of order 2, we have a non-trivial representation from G mod N to minus 1, 1. An isomorphism from G mod N to 1 minus 1. So that's going to give you a representation which is other than the trivial representation. And now the previous idea of lifting will give me a degree 1 representation other than the trivial one. So already I have accounted for 2 degree 1 representation and 1 degree 2 representation. Right? So we got 3 of them. How many more? Now we will state a theorem that will be proved later. Suppose, for example, phi and psi are 2 representations, then phi is equivalent to psi if and only if trace phi g equal to trace psi g for all g. Okay, so the number of irreducible representations is the number of conjugacy classes of G. The number of irreducible representations will be equal to the number of conjugacy classes of G. So if d1, d2, dk are the degrees of all the irreducible representations up to equivalence, then the order of G is going to be the sum of the squares of these things. So now I'm stating a number of results which you're going to use later on. And finally, the degree of the representation must divide the order of the group. Now, these things put a severe restriction on the possible irreducible representations of a finite group. So, what is the order of a dihedral group? It is 10. So, what are the possible orders for the degrees of irreducible representation? 1, 2, 5, and 10. That's all. Now look at this equation. Order of G is d1 squared plus d2 squared plus dk squared. This also obviously 10 is out. Even 5 is out because 5 squared is 25. Correct? So 10 must be equal to a sum of squares. Correct? So already we have 2 representations of degree 1 and we have 1 representation of degree 2. So 2 squared is 4. 4 plus 1 plus 1 6. We only have room for how many conjugacy classes are there? There aren't too many conjugacy classes either. So, in the case of the dihedral group, 10 will be equal to summation di squared, d1 equal to 1 trivial representation. There are 4 conjugacy classes. So there are only 3 more representations. So, 9 will be d2 squared plus d3 squared plus d4 squared. So, the dj's have to be 1 or 2. It can't be 5. The only possibility is that d2 is 2. D2 is 1 because we remember we have one more degree 1 representation. D3 and D4 are 2. Okay. So with using the normal subgroup, we got one more degree 1 representation. So D2 is 1. There remains the task of finding the last, and we got a degree 2 representation, the geometrical one. There remains the task of finding this last one, which is a degree 2 representation. Exercise, there are 4 conjugacy classes for the dihedral group of order 10. Now this group has trivial center. This group, prove that the dihedral group of order 10 has trivial center. So it has only one self-conjugate element, namely the identity. There are 5 elements of order 2 forming one conjugacy class. Question mark how? These are like basic Syllo's theorem and all those kinds of things. Try to give arguments, try to give 2 arguments, a geometric one besides an algebraic one. For example, for a group action, stabilizer of x equal to stabilizer of y, then x and y are conjugates. So draw the pentagon and tell me how the elements of order 2 form one conjugacy class. Give a geometrical argument to show that there is only one conjugacy class, rather than an algebraic argument. Algebraic argument can also be followed. Elements of order 2 must form 2 conjugacy classes. Look, the trivial element forms one conjugacy class. The 5 elements of order 2 form one conjugacy class. How many are been accounted for? 6 elements. How many are remaining? 4 elements. The number of elements in the conjugacy class must divide the order of the group. So the 4 elements cannot form one conjugacy class. They must form 2 conjugacy classes of 2 elements each. Okay. So, so that's how you cut down the number of possibilities. Now let chi be the non-trivial representation of degree 1 and phi be the degree 2 representation obtained above. Then phi times chi is again a degree 2 representation. Unfortunately, phi times chi is equivalent to phi. Well, let's calculate the traces. We prove that the trace of phi times chi is the same as trace of chi. Sorry, trace of uh, since this chi is one dimensional and trace is linear, trace of phi g times chi g is chi g times trace of phi g. Suppose if g is in the suppose for example g is the normal subgroup. Okay, then you know that because that is that because this chi is a non-trivial representation, it will send all the elements of the normal subgroup to 1 and it will send all the elements outside the normal subgroup to -1. So chi of g is 1, and if g doesn't belong to n, then g is an element of order 2, and so it's conjugate, and so it's going to be conjugate to this, and so the matrix has trace 0. So by looking at the traces, we can check that these. So we are not. So we got to do more work in order to prove the other degree 2 representation. Predicting its existence was easy, but realizing it can be challenging. Let us see how to do it. Now each element of the group is a permutation of the vertices of a regular pentagon, right? Each element of the group is a permutation of the vertices of a regular pentagon. And the group can be written as 5 cycles, a 5 cycle 1, 2, 3, 4, 5, rotation through angle 2 pi by 5, and it iterates. And these kinds of one vertex gets fixed, and pairs of other two vertices get flipped. And so now these are, and so you can look at the corresponding permutation matrices. That is, simply take the standard representation of S5 and restrict it to G. And we know that this permutation matrices, representation by permutation matrices, is reducible because 1, 1, 1, 1, 1 transposes a common eigenvector, and I can take the C linear span of them. And every permutation matrix is a unitary matrix. Prove that every permutation matrix is a unitary matrix, and so this representation is a unitary representation. So W perp is also an invariant subspace. Okay, so we get a degree 4 representation, correct? Namely rho from G to GL W per. Then we must compose. Then this row must decompose because 4 doesn't divide the order of the group. So it must decompose into a sum of irreducible representation. Chi naught is a one-dimensional representation which is trivial. And suppose rho decomposes as A copies of chi naught, B copies of chi, and C copies of phi. How many copies can be there? A, B, C can be 0, 1, or 2 because the dimensions have to add up, no? Dimensions have to add up. And now you calculate trace of rho G will be A times chi naught, A times the trace of chi naught, but the trace of chi naught is a trivial one, so A is A. B times trace of chi G, C times trace of phi G. But the trace of a permutation matrix, what you're taking the ortho complement, right? So 1 was an eigenvalue, so the whole permutation matrix -1 you have to take. So for the phi cycle, the trace is 0, and when I subtract 1, I get the trace to be -1. And so trace of and trace chi G is trace for the other permutation that we have for the one that you lift. This is going to be 1 because this phi cycle belongs to the normal subgroup. And so we get this equation -1 equal to A plus B plus C, C times trace phi G. And what is trace of phi G? This phi G, trace of phi G is 2 cos 2 pi by 5 for the two-dimensional representation. Remember the 2 by 2 matrix? Cos minus sine cos, 2 times cos 2 pi by 5. This is not possible because all three are positive. So this decomposition must provide yet another degree 2 representation which is not equivalent to phi. Okay. So this is a notorious example. So some important remarks. following Mashker's theorem concerning the block matrix avatar of Fiji. We have used this above, and we shall not elaborate on the direct sum of copies of chi naught, of A copies of chi naught, B copies of chi, C copies of phi. It's the meaning of this should become clear. Is this correct? Yes, guys.
Yes, sir.
Then there is exercise 3.8 on page 25 of Steinberg's book. Okay. Now, so this example on the dihedral group, I would like you to read this part very carefully. I may have gone a little fast, and just by listening to me, you can't get all the nuances. So I think you will have to work it through. This, particularly this trace calculation, I would like you to work out in detail. Okay, because this kind of calculation will come up again and again in the theory, right? So can you do it?
Yeah, yes.
Please do the details of this particular thing. Okay, and then we get this exercise 3.8 on page 25 of Steinberg. Consider the representation from S3 to GL4C. Remember, we had a two-dimensional representation of S3. You just put them together, string them together. The same representation, two copies of it. Okay. Then this particular this is a two-dimensional representation, and I took two copies. The matrices do not have a common eigenvector. Prove that the matrices do not have a common eigenvector. So the theorem that so here this representation is reducible with a direct sum of two representations when the matrices don't have a common eigenvector. So the theorem that we proved for a degree 3 representation or a degree 2 representation, if it is reducible, then all the matrices must have a common eigenvector. That result is clearly false for 4-dimensional degree 4 representation. That is what this is pretty easy, and I worked it out. And another exercise on page 24 of Steinberg. And this is something that so you take a representation and you define the fixed subspace of Vg. Okay, what is the fixed subspace of Vg? Fixed subspace of Vg consists of vectors which are fixed by all the matrices. So 0 is obviously a fixed subspace, correct? And 0 is obviously a fixed subspace. There are vectors which are fixed by all the Fijs. So the eigen subspace corresponding to eigenvalue 1. So all the matrices have eigenvalue 1 and the eigen subspace. Of course, if 0 is the only one, then 1 is not an eigenvalue. If there is a non-zero vector with this property, that would immediately mean that all these linear transformations must have 1 as a common eigenvalue. That's a rather strong condition. It may happen that usually the fixed subspace will be only the trivial element. Okay, so what you do is you take a vector v and you average this vector 1 upon the order of the group times phi hv, and take the set of all such vectors that you get. That will form the fixed subspace of the representation. And you've got a projection mapping from V to this fixed subspace. Simply take this V and map it to the average. So in the context of invariant theory, this idea, this is known as the Reynolds operator. Okay. So we shall see examples of S4A5 later in chapter 3. Then we talk about parliament of irreducibles. Given a finite group, we shall see that up to equivalence, there are only finitely many irreducible representations. The family consisting of exactly one irreducible representation out of each equivalence class of irreps will be called a parliament of irreps. As in the case of the dihedral group, one is interested in a direct sum decomposition of a given row in terms of its irreducible components, taken out of a parliament of irreducibles. So, what is the parliament of irreducibles? The general theorem is that up to equivalence, there are only finitely many irreducible representations, d1, d2, dk. What is the relation between the d's? d1 squared plus d2 squared plus da 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 plus dk squared is the number of elements in the group. Each di must divide the order of the group, and the number of irreducible representations exactly matches the number of irreducible representations up to equivalence exactly matches with the number of conjugacy classes in the group. These are the rigid constraints on the number of irreducible representations. And the idea is to take one irreducible representation, form a parliament consisting of exactly one irreducible representations out of each equivalence class of irreducible representations. And here are some references. The Fuglade-Putnam theorem, the reference is John and Horn and Johnson's. Lederman's book, which I already talked about in chapter 0. Lehrer and Taylor, from which unitary group reflection groups, from which I picked up that example of a degree 2 representation of S4, and Steinberg's book again, which I talked about in chapter 0. So, any questions, please, on this? I've been a little fast with this dihedral group, but again, that's something that you need to really read the notes very carefully and go through it. There's no point in me, droning over this. You need to take this. You need to try these out. Suppose, for example, if you take this ortho complement, you take the standard representation, restrict it to the dihedral group, take the ortho complement of W, you get a 4-dimensional representation that cannot be reducible because 4 doesn't divide 10. It must split. It must split as a sum of 2 degree 2 representations. Why it can't split as A times? So suppose it splits as A times the trivial representation, B times the non-trivial representation of degree 1, plus C times the geometrical degree 2 representation, and then you calculate the trace of various matrices, the various permutation matrices, and you'll have to subtract a -1 because you're taking the ortho complement, right? This vector will correspond to the eigenvalue 1, and you're taking the ortho complement, so you have to remove that. So you have to remove that eigenvalue from the trace. The eigenvalue 1 must be removed from the trace. That's why you subtract off. And after you subtract, so you have to do that for all the for the 2 different types of matrices, the 5 cycles that you get, and this other one, 2 5 5 2. Like if you fix one, like if you draw this symmetry axis, and then there's a transposition of 2 5 multiplied by a transposition of 3 and 4 with 1 fixed. For those matrices, what are the traces? You have to check. So what are the traces for that? For example, can you tell me? Suppose I take the symmetry axis passing through this vertex 1. Then what are the trace? Hello. 1 is already fixed with the permutation matrix that you have. In the 1-1 position, you have 1 already. The 2-2 position gets displaced, and the 5-5 position gets displaced because there's a transposition of 2 and 5. The 3-3 position and the 4-4 position, the ones there get displaced. So the trace of the permutation matrix for this one is 1. And so when I subtract 1, I'm going to get 0. Correct? That's what I written here. You have to try those. Whereas if I take the rotation by angle 2 pi by 5, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. So all the diagonal elements get displaced. So trace is 0. So trace is 0, and I have to subtract -1. So the trace becomes -1 for the 5 cycle. Is this clear? Yeah?
Yes.
So that's the kind of calculation I want you to do. And that kind of calculation will give you that this kind of thing is impossible. You cannot get. There has to be something other than these the 3 that you already have in the decomposition of this row. Another thing that you have to rule out is that it may happen that this row is simply phi plus phi, but that also cannot happen because that will mean that A is 0, B is 0, and C is 2. That also is not possible. A is 0, B is 0, and C is 2. That's also not possible. A equal to 1, B equal to 1, and C equal to 1. That's also not possible. C is 0 and A appearing 4 times. That's also not possible. So we have tried all possible. So we are assuming that A times the trivial representation, B times the non-trivial representation of degree 1, C times the representation of degree 2. We have tried all these combinations. All these have been included. All these cases have been included in this discussion. There has to be one more over here. Okay. Is this clear? So there must be one more representation of degree 2. What is that representation? We have to find out. Okay. I think I'll stop the lecture here.